It's Workbench Quagmire. It's day 82 of our free Code Camp Python certification in 100-ish days. We're back to theory sections here. We're in our new, what section are we in here? We're in our graphs and trees section here. So we got some theory sections, and then we got a workshop, lab, quiz. We are done with the certification projects. So we had 1, 2, 3, 4, and Tower Hanoi was our last one. So here we'll just have reviews and quizzes, and then we have, I think, only one theory section and one lab, and then the big review for the certifications. So let's jump right into our what are graphs in computer science. What are graphs in computer science? Graphs are data structures used to represent the connections or relationships between objects and entities. They're often used to model networks. The types of networks that can be modeled with graphs include social networks, transportation networks, communication networks, and even recommendation systems. For example, graphs can represent connections between users on social media platform or connections between cities on a road network. They are very versatile. A graph is often represented as a collection of points or circles connected by lines. These circles and lines represent the two main components of a graph: nodes and edges. Nodes are known as vertices, represent the objects or entities that are part of the network modeled by the graph. They could be users, products, stations, cities, or any other entities in the model. In this example, nodes are represented as circles and are labeled with letters A, B, C, D, and E to distinguish them visually. Edges are the connections between nodes. If two nodes are connected by an edge, that means they're somehow connected in the network. In this example, there are 5 edges connecting the different pairs of nodes. Node A connected to node B is connected to node A, C, and D, and so on. 1, 2, 3, 4, 5. Yep. The specific meaning of the connection will depend on the context. It may be physical, like a real road that connects two cities, or it could be more abstract, like the connection between two users on a social media platform. If the nodes are directly connected by an edge, like node A and B, in this example, they're known as adjacent nodes. Type of graphs. There are different types of graphs with different characteristics and application. Let's go over some of them. Undirected graphs. Undirected graphs are graphs where the edges don't have a specific direction. This type of edge is usually represented with a straight line between the nodes. This means that there's an edge connecting node A and B, and the connection works in both directions, from node A to node B and from node B to node A. Depending on the network that is being modeled by the graph, this connection can have different meanings. For example, if you're modeling connections between users of a social media platform, this means that user A is connected to user B and user B is connected to user A. This connection is bidirectional. Directed graphs, as opposed to undirected graphs, are graphs where the edges do have a specific direction. There is a connection from node A to node B. That doesn't necessarily imply there is a connection from node B to node A. The edges of a directed graph are often represented as straight lines that end with arrows to indicate the direction. Here's an example. In this graph, you can go from node A to node B, but not from node B to node A because of the direction of the edge. For example, if you're modeling a road network, this would be helpful to model one-way streets or roads. You can go directly from city A to city B through the road, but not from city B to city A. You'll need to take a different route. If there is a two-way connection between the nodes of a directed graph, you can represent this with two directed edges between them. Here's an example. You can go from node B to node D, and from node D to node B, because there are two edges connecting them, but each edge has a direction. Vertex labeled graphs. In this graph is a graph in which each node is associated with a label or identifier in addition to its data. These labels are used to identify the nodes, represent them visually, and store additional information about them. For example, in transportation network graph, nodes could be cities and their labels could be their names, coordinates, or any other characteristic that would be helpful for the purpose of the model. Cyclic graphs. Cyclic graphs are directed graphs with at least one cycle. A cycle is a path that you can follow through the edges of a graph that will take you back to the initial node where you started. In this example, we have a directed graph. If you look more closely, you'll notice that it has a cycle. If you were to start at node B, go to node C, then node D, we can go back to node B again through the directed edge. This is a cycle, so this is a cyclic graph. Edge label graphs. In edge label graphs, edges are associated with labels. These labels are usually drawn next to their corresponding edges. And weighted graphs. Weighted graphs are specific types of edge label graphs in which the labels on the edges represent values that can be compared and used to perform arithmetic operations. Some edges have a higher weight, while others have a lower weight. These weights represent the cost of the edge. For example, you may represent the distance between two cities or the time it takes to get from one city to the next. This is an example of a weighted graph. We write each weight next to its corresponding edge. The cost of going from node B to node D is 3, and since it is undirected graph, that's the same cost as going from D back to B. 7, 6. Directed acrylic graph. Another very common type of graph in computer science is the directed acrylic graph, in which a directed graph with no cycles. Here's an example. It's a directed graph because each edge has a direction. It's acrylic because it doesn't have any cycles. Why? Notice that if you start at a specific node, you cannot go back to it because of the direction of the edges. So where the cycle was last time, we can go A to B, we can either go to D to C, but it doesn't matter which one we're going to D eventually into E. So a disconnected graph is the last type of graph that we'll cover in this lesson. In the disconnected graph, a disconnected graph is a graph with two or more groups of nodes that are not connected by any edge. In the real world example would be a social media network where you have two or more groups of people who don't know each other and who have no friends in common. This is an example. The first component has the node A, B, and C, and the second component has the nodes D and E. These components don't have any edges between them, so this is a disconnected graph. You can implement graphs in a variety of ways, including sets, functions, and arrays. You'll learn more about this in the coming lessons. Understanding graphs and the characteristics of different types of graphs is essential for solving a wide range of problems in computer science and other fields. What is a graph in computer science? A data structure used to represent relationships between objects? Nope. A mathematical equation? Nope. A visual representation of data? I think so. A programming language? Definitely not. Actually, it's probably A, or the first one here. Two main components of a graph are points and lines, vertices and nodes and edges. That's correct, and elements and vertices. What is a directed graph? A graph where the edges do not have any direction. That's not true. A graph where the edges have a direction. That's true. A graph where more nodes than edges. That's not true. And a graph with more edges than nodes. So it's 2. Let's see if we got the first one right. We did. All right. How do depth first and breadth first search work? As you start working with data structures and algorithms, you'll soon realize that one of the common operations that you'll need to perform is visiting each node. This process is known as traversing the data structure. Traversals are used to do something with every single node in the data structure, like printing their values, finding a specific value, or performing certain operations on the nodes. By systematically visiting each node, you make sure that the process won't skip any nodes. How do you determine the order in which you should traverse the data structure? Where should the process start, and how should the next node be selected? Without a clear way to traverse the data structure, going through it would be like walking through a maze without a specific path to follow. That's where algorithms like breadth first search, BFS, and depth first search, DFS, become really important. They are commonly used to traverse graphs and for finding a path between two nodes. When they are used to traverse a data structure, they define the order in which nodes should be visited to make sure that none of them are skipped. Let's start with the breadth first search, or BFS. BFS is an algorithm that visits all neighboring nodes before moving on to the next level of the graph. It can be used to find the shortest path between two nodes in an unweighted graph because it analyzes all the nodes at each level, so it finds the path with fewest edges first. This algorithm is commonly implemented using a queue data structure to keep track of the nodes that have been visited. Queues follow the FIFO, first in, first out method, where the first node that is added to the queue is the first one to be removed. The algorithm works like this. You start with a specific node. That node is marked as visited and added to the queue. While the queue is not empty, the current node is removed from the queue, dequeued. Then, for each one of its neighbors, if the neighbor has not been visited, it is marked as visited and added to the queue. One important consideration is that since breadth first search, or BFS, requires storing a queue in memory, this queue may have a large number of nodes. The space requirements of this algorithm may be considerable, and this is especially true for graphs with large numbers of nodes on the same level. Let's see an example of BFS applied to a specific type of graph called a tree. You will learn more about trees in the upcoming lesson, but they are essentially graphs with no cycles, where nodes are organized in a hierarchy and cycles are paths that start and end at the same node. Let's apply the BFS algorithm to the tree. So we have 1, 2, 3, 4, 5, 6, 7 nodes. We would start at the root of the tree, node A. We add A to the queue and immediately mark it as visited. So we have a list with the nodes and we have a set with visited. So that's probably important. We dequeue node A when it is step 2. We dequeue node A. We add its unvisited children, node B and C, to the queue and mark them as visited. So now we have A, B, and C visited, and the queue contains B and C. The order in which nodes on the same level are added to the queue is defined by the implementation of the data structure and the order in which the edges, connections, are stored in the graph representation. If the implementation is consistent, the specific order in which the nodes at the same level are traversed will not affect the correctness of the algorithm. It will still visit every node level by level. Step 3, we dequeue B. We add its unvisited children, D and E, to the queue and mark them as visited. So B, D, and E. Step 4, we dequeue node C. We add its unvisited children, F and G, to the queue and mark them as visited. Step 5, we dequeue D. This node does not have any unvisited children, so nothing changes in the visited set. Step 6, E is dequeued. It doesn't have any children, so there's nothing to change in the visited set. So it just repeats for F and G. And then finally, the queue is empty. The traversal is complete. The nodes were traversed in this order: A, B, C, D, E, F, and G. C, D, E, F, and G. Notice that the algorithm visits the nodes per level. We start at node A and then move to the next level and visit B and C, then to the next level and visit D, E, F, and G. This is a core principle of breadth first search. Depth first search. While breadth first search visits all the neighbor nodes at the same level, depth first search follows each branch as deep as possible before it backtracks. You can imagine this algorithm is exploring a maze by choosing a specific path and following it until you reach a dead end or an exit. If you reach a dead end, you go back and choose a different path. Depth first search is commonly used to solve puzzles with single solutions, detecting cycles in a graph and finding connected graph components. This algorithm can be implemented using recursion or a stacked data structure to keep track of the visited nodes. Stacks follow the last in first out method, where the last node that has been added to the stack is the first one to be removed from the stack. The algorithm works like this. You start at a specific node. That node is marked as visited and added to the stack. When the stack is not empty, the current node is popped, removed. This is when we visit or process it, for example, by printing its value. Then all of its unvisited neighbors are marked as visited and added to the stack. One of the limitations of this algorithm is that it's not always guaranteed to find the shortest path between two nodes in an unweighted graph. Let's see how this depth first search will apply to our tree example. So step one, at the start of A, we're at node A, we mark it as visited and add it to the stack. Step 2, we pop A from the stack, then we add its unvisited children, B and C, to the stack. We'll add them in reverse order, C then B, so that B is on top, LIFO, and will be processed next. We also mark them as visited. We pop B from the stack. Then we add its unvisited children nodes, D and E, to the stack in reverse order, E then D. We also mark them as visited. We pop D from the stack. And this node is no children to add to the stack. So now we just have C and E. And we have visited A, B, C, D, and E. Step 5, we pop E from the stack. This node has no children and to add to the stack. So now we're down to C. We pop node C, then we add its children, F and G, in reverse order, G then F. We mark them as visited. Then the last two steps is we pop F and we pop G, but they don't have any children, so we don't add anything to the visited or to the stack. And when the stack is empty, the traversal is complete and all nodes have been visited. The algorithm visits the nodes in this order: A, B, C, B, E, B, A, B, A, C, F, C, G. Notice how we start at node A, then move all the way down to the tree to node B, then node D and E before moving up again to node C, then node F and G. This is a core principle of depth first search, traversing full paths before backtracking and finding other paths. In this case, we solved this example using a stack. Alternatively, depth first search can be implemented using recursion, where the function passes the current node and then calls itself for each of its unvisited nodes. The full call stack implicitly manages the LIFO, first in first out order. Both breadth search and depth search are essential algorithms to traverse graphs and trees. Breadth search explores nodes level by level, and it's perfect for finding the shortest path of an unweighted graph. On the other hand, depth first search follows one branch as deep as possible for backtracking, which is perfect for solving mazes and detecting cycles. Understanding their pros and cons is helpful for choosing the right one in a particular problem. So, this following data structure is commonly used to implement a standard BFS algorithm. So in this one, it's a queue. Which of the following statements about DFS is true? Depth first is guaranteed to find the shortest path between two nodes in an unweighted graph. No, that's BFS. Depth first search visits all the neighbors at the current level. That's BFS. Depth first search is always more space efficient than BFS. I don't think he even talked about that. and depth first search is typically implemented using recursion or a stack. That's true. If you want to find the shortest path from a starting node to a target node in an unweighted graph, which algorithm would be most suitable? That would be breadth first. Check my answer. Yay, we got it correct. All right, that's all the theory sessions we're going to pack in on this video. Next time we will do this how do matrices and adjacency lists work. Thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time.